previous lecture, we looked at the concept of macrostates and microstates. Let's get settled down. Excuse me, let's start. We should be able to start at some point in time. So I will give you a very quick recap of what we discussed the other day. Suppose we have two atoms. We have two atoms, which means we have 6 oscillators in total. This is atom A. This is atom B. Of course, these are harmonic oscillators. The energy levels are quantized. And these two atoms are brought close to one another. And there is a total of 4 quantums of energy. Q is 4. The number of oscillators, total oscillators is 6. The number of oscillators in A is 3. The number of oscillators in B is 3. And these 4 quantums have to be arranged within the 6 oscillators. So we started making a table as well. So what is the macrostate of the combined system? Can anyone tell me what the macrostate is? What for? 4 quantums distributed within 2 atoms. Now these atoms were separate, now they are brought close to one another. And what we want to see is how the quantums are distributed. ठीक नहीं है ना, आवाज सही नहीं आती. इसके सेल बदलने पड़ेंगे. So we're going to make a table and follow these steps very carefully, because this is going to set the stage for the second law of thermodynamics. I've already drawn this table again, but I would like to reiterate to make the narrative complete. So the first column is number of quantums in atom A, and I call this QA. Then the remainder of the quantums would be in atom B. So I make a column QB. This will of course be 4 minus QA, because the remainder of the energy will be in the second atom. Now I make a column, given that I have QA quantums in atom A, how many microstates for the system A are possible? How many ways do exist in which I can arrange those QA quantums just in atom A? Alright? So I make a column omega A. I make a column omega B. And I make a column in which I multiply the number of microstates omega A with omega B. So I can have 0 quantums in A, which means 4 of them will be in B. I can have 1 in A, 3 in B. I can have 2 in A, 2 in B, 3 in A, 1 in B, and all 4 of them could be in A, and there will be none in B. So these are the different ways in which energy can be distributed within the two atoms. I am keeping the total number of quantums constant, which means the total energy is constant. These two atoms can exchange energy only amongst themselves, and they cannot exchange energy with the surroundings. This means the total energy of the system is constant, and the system is called a closed system. Now I have to find the number of ways in which 0 quantums could be introduced in atom A. So what should I write here? 1. And what should I write here? I have 4 quantums, and all 4 of them go into B. What should I write here? 15. This is 15-1. Now if I have 1 quantum in A, how many ways exist? 3. There are 3 ways in which 1 quantum could be introduced into atom A. The 1 quantum could be here, or it could be here. So one possibility is that there's 1 quantum here and 0 quantums in these oscillators. The other possibility is the 1 quantum is here and there are 0 quantums here. I'm just, instead of drawing it over and over again, I'm using different colors. So don't be confused. The third possibility is that the 1 quantum is here and there are 0 quantums in the other oscillators. Alright? So there are 3 ways in which the 1 quantum could be placed in atom A. Is everyone with me on this? Any confusion? I can repeat if you want. Don't be shy, because things are going to get more complicated. Any confusion? So I put 3 here, and I would put something here which would mean the number of ways in which 3 quantums could be placed in atom A, in atom B, and there are 10 ways in which that can be achieved. So I put 10 here. This would be 10, 3. This would be 6, 6. We already made this table in our previous lecture. Now, these are the number of microstates associated with only atom A. These are the number of microstates associated only with atom B. But for the total system, which comprises both the atoms, what we are interested in is looking at the energy distribution within both the atoms. So we would like to find the number of microstates in the total system, and for that, these are the possibilities for A, these are the possibilities for B. So we have to multiply these numbers. So there are 15 ways really in which atom A holds no quantum and atom B holds all the 4 quantums. There are 15 ways in total. So you multiply this with this. These are the subsystems. A is a subsystem, B is a subsystem, and this is the total system. Alright? So these are subsystems. and this is the total system. I multiply these numbers, I get 30 here, 36, 30 again, and 15. So if I were to place 4 quantums and distribute them, there are different possible microstates. There are 15 microstates in total, which would have 0 quantums in atom A and 4 in B. There are 36 microstates or 36 possibilities in which 2 of them will be in A and 2 of them will be in B. There will be an equal distribution of quanta in most of the cases, because all of these microstates are equally probable. They're equally probable, hence the higher the possibilities, the more will be the probability. So there are 36 possibilities in which the quanta are equally shared. There are 30 possibilities in which A has 1 quantum and B has 3 quantums. So do you understand what this table means? Now if I would like to make a graph of this, what I would like to make, let's first make a graph of sigma A versus QA. Alright, I'm going step by step so that you follow each and every step. I'm not going to miss out any details because this is very important. Now QA can be 0, 1, 2, 3 and 4. And I'm just plotting sigma omega A. So omega A is this. I'm just looking at the subsystem. 1, 3, 6, 10, 15. Alright? Just a graphical representation of this column. Now let's make another graph in which I would like to plot sigma omega B versus QB. QB can be 0, 1, 2, 3, 4. What kind of graph will I get? I'll get the same graph because I start counting from here. 1, 3, 6, 10, 15. I'll get the same graph. So I would somehow I can also plot sigma B versus QA. It doesn't matter. It's just that when QA is 4, QB is 0. So if I somehow make a scale which is inverted, this is a QA scale, and I would like to plot the same information onto this graph, I would make another scale, QB, and I would put 0 here, 1 here, 2 here, 3 and 4. So I could plot this information onto this graph. It doesn't matter. So this will be 1, or I can plot it side by side. Okay, 1, 3, 6, 15, 10 and 15. So the blue is a plot of omega b versus QA or QB. If you consider this axis, it's versus QB. If you consider this axis, it's versus QA. Because QB and QA are related, the scales are inverted. So I hope you understand this graph now. Now if you look at these graphs, what it's showing is that sigma A is increasing with QA, sigma B is decreasing with QA, right? But what we are interested in is omega A times omega B, the total number of microstates for the combined system. For this, we'll have to multiply these columns and we get these results. So let me plot a graph of sigma A, sigma B versus QA. I just need to plot it versus either of these quantums because we know the total number of quantums. If I know QA, I know what QB is. If I know QB, I know what QA is. So I'll make another graph in which I plot omega A, omega B versus QA. I have 0, 1, 2, 3 and 4. I can think in my head that if I had a QB graph, this would be 0 on the QB graph, and the QB graph is increasing from right to left. The QA graph is increasing from left to right. So I plot omega A, omega B, 15, 30, 36, 30 and 15. I'm going really slower than what I would have liked, but I really want you to understand and enjoy what's going to come, because I enjoyed it when I read it. Now you see, if you look at this graph, which is, if you look at the combined system in which you have two atoms, the higher number or the highest number of microstates are associated with a 2 by 2 or a 50-50 sharing of energy. Half the quanta belong to atom A and half the quanta belong to atom B. So in about 36 over 126% of the times would the quanta be equally shared. But there is also a finite probability. The height of these curves tells you the probability. There is also a finite probability that QA is 1. This probability is 30 over 126%, right? There is a finite probability that QA shares 3 quanta, that is 75% of the energy, and B has 25% of the energy. It's also possible that A has, this is 15 over 126. It's possible with this much probability, it's about, I think, 10 or 11%, that QA is 0, which means A does not hold any energy. All the energy belongs to atom B when the two atoms have come close together and interacted with each other. But the higher probability is associated with an equal sharing. But the system that we've considered so far is not really what we see in our daily lives, because we hardly see two atoms coming close to one another and seeing how their energy redistributes. What we really have is very large objects that come close to one another and they interact and they share energy, right? So really this is a toy model. This is to get you motivated. What we really have is two large objects that are coming close to one another. And now we would like to see how they share their energies. So we'll use exactly the same techniques and consider a more realistic, still it's not a very realistic model because still we're dealing with small numbers of atoms, but I cannot use a very large system because then I don't have the computational capabilities to show you the simulation, because then the computation gets very long. So the other day I gave you an example of a solid comprising 100 atoms coming close to a solid that was made up of 50 atoms. Alright, so it's a bigger solid. It's not one atom, 100 atoms, 300 oscillators, 50 atoms, 150 oscillators, and the total energy that has to be shared is, say, 100 quantums. So now total energy of 100 quantums has to be shared amongst these objects. Now I make an exactly similar graph, an exactly similar table to start off with. I have QA, I have QB, I have omega A, I have omega B, and finally omega A, omega B. Now QA goes from, what's the range of QA? 0 to 100. So this can be 0, 1, 2, 3, up to 100. Correspondingly, QB is, if this is 0, what is QB? 100, 99, 98, 0, 1, 2, and so on. Now I have to calculate the number of ways in which 0 quantums could be arranged in atom A. How many ways? Someone at the back? One. This is just one way in which 0 quantums could be arranged in 300 oscillators. All the 300 oscillators will have 0 quantums of energy. So there's only one way. But this is a very large number. I don't know as yet. If I have 0 quantums in B, then my omega B will be 1 here. So another question I would like to ask, if I have 1 quantum in A, what will be the value of omega A? 3? I have one quantum arranged in 100 atoms, which means 300 oscillators. How many ways are there? 300 ways. So these rows are easy to fill, but then it starts getting more complicated and these numbers start increasing. But I also showed you a formula the other day that we can use. If we would like to calculate omega A, this is equal to the number of quantums in A plus the number of oscillators in A minus 1 factorial divided by QA factorial NA minus 1 factorial. So if I would like to calculate what goes here, I would take QA equals to 2, sigma A QA is 2, the number of oscillators is 300. I would take 2 plus 300 minus 1 factorial divided by 2 factorial divided by 300 minus 1 factorial. And I would use a computer to solve this, or a calculator that can go to a very large number of significant figures. Ali, इसको ज़रा चला दें please. Alright, while this boots up, I can also find omega B. Omega B will be QB plus NB minus 1 factorial divided by QB factorial divided by NB minus 1 factorial. If you would just like to look at the screen over there, I've moved myself away from your screen so that you can have a better look. So, how many quanta do I have? I have 2 quanta in 3 alright, so I use this formula by putting the numerator 2 plus 300 minus 1 and I put 2. This is a very large number. So this is just the MATLAB format for calculating this formula. So I get a very large number here, which is 45150, and this number keeps on increasing because the number of quanta is increasing, and when the energy is increasing, the number of possibilities in which that energy could go into atom A is also increasing, whereas this number will keep on decreasing because the number of quanta in B is decreasing. So this is increasing and this is decreasing. So just to give you an example, if I have QA equals 100, all the 100 quanta of energy are in atom A. Let's find out what the answer is going to be. So I put 100 here for the number of quanta, 300 is the number of oscillators, and I put 100 here. Now this is a huge number, a really huge number. Your normal calculators can't calculate this. So it's about, this number is about 1.6 into 10 raised to power 96. So this is larger than the number of atoms in the universe. It's such a large number. If I'm standing here and I'm 1 unit, I would like to express how long do I have to travel to traverse these units. I would have to move around the universe, the known universe, several times. Such a large number. So there is a huge variety of ways in which the 100 quanta can be distributed in atom A. But the problem is that there is only one way in which 0 quanta can be introduced in atom B. So this extra large number, prodigious number, very large number is being multiplied by a small number. The situation is exactly opposite here. This is going to be a very large number of the order of 10 raised to the power 96. Now this very large number is being multiplied by a small number when you look at the total system. So one has to construct this column and then make this column. And I've written a computer code that does this. I've also uploaded it. It's in MATLAB. You're very familiar with MATLAB, so it's not going to be a problem. I've already shown you this code, so let me just run it. Now focus your attention please on these graphs. Let me just check if we can look at these from the back. They are visible? They're clear? You can't see the font or?
It's visible.
It's visible, right? You can't just see the font, but I'll tell you what these graphs are. You see, this graph here, this one, is a graph of the number of quanta in A, which means this column is on the x-axis and omega A is on the y-axis. So it starts off from a very small number. It starts off from 1, a very small number, and it goes to an astronomically large number. It's 10 raised to the power 96 here. It starts from a very small number and rises super fast, but rises at the very end. Right. So this graph should be clear. Now if you look at system B, I've plotted it again versus the number of quanta in A. This starts off from a very large value, an extra large value, but suddenly drops and goes to almost 0. It goes to infinitesimal, to nothing. Now here what I've done is I've plotted this column, omega A multiplied by omega B versus the number of quantums in A. Now this looks like a more reasonable graph. Let me try zooming in on this so that you can have a, I want to explain this in a bit of detail. Do you understand what I've done computationally? It's just instead of doing this problem for this large number of oscillators on the blackboard, I've done it on the computer. And that's what statistics is all about. Alright, I can't do this, so I think you're too early for Friday's class. Alright, so this is a plot of omega A times omega B, which is this column versus the number of quantums in A. Now if you look at this graph carefully, it's peaking somewhere, and it's peaking at a particular value of Q, around 67, and this scale, this value is about 10 raised to power 110. So the probability, or this variable, is extremely large. I cannot say it well enough. Large here means ultra large. It's prodigious, it's very large. So this is very large, which means that if the probability associated with having 67 at quanta in object A and 33 quanta in object B is extremely large as compared to anything else. Since this number is so large, which means the number of microstates in which 67 quanta go in A and 33 quanta go in B, the probability for this happening is so large as compared to anything else that this large probability is actually the only thing that can happen. So it's such a large probability that it becomes very close to to the only possibility. Now let me say this again. The probability is so large as compared to the alternatives that it becomes practically speaking, the only possibility. Because now we are dealing with very large systems. We are dealing with the law of large numbers, we're dealing with statistics, and we're dealing with probabilities. The probability that 66.66% of the energy is in atom A and the remainder is in atom B is so large as compared to any other distribution that the most probable distribution becomes almost the only possible distribution physically, in practical sense of the word. So this is such an important statement. I'm going to turn on the lights and write this down on the blackboard. When dealing with large real life objects, the highest probability distribution of energy really becomes the only, I'm underlining, physically plausible possibility. No questions? Yes.
When you're saying highest probability distribution, you mean 1 point, or you mean the entire curve at the very top?
The highest probability distribution of energy, that is that particular distribution of energy which has the highest probability, which is the modal point of this curve, which is the topmost. But remember that there is a finite probability which is also exists for neighboring distributions. So what happens if I increase, now compare this graph with the graph here. What's the difference that you observe? This is much sharper because the energy is higher and the size of the objects is higher. Now, dealing with 100 atoms is still not really macroscopic. 100 atoms is still a small number. If I increase the atoms to what really is plausible, that is, I have, say, 10 raised power 20 atoms in a solid and 2 atoms that come close together, then the width of this peak is going to decrease. It's going to sharpen. Let me finish that answer first. So, if I have 1000 quanta in 10 raised power 10 atoms, I will get a certain probability distribution. If I have the same number of quanta in 10 raised to power 15 atoms, I will get a sharper probability distribution. If I have 10 raised to power 20 atoms, I will get an even sharper probability distribution. So if I keep on increasing the number of atoms or I keep on increasing the number of quanta, this peak sharpens and sharpens. So the probability exists only at a certain point, around a certain point, and the probability is magnificently huge there. So anything else is incomparable. It cannot even be mentioned as compared to the probability at which this peak is occurring. So wherever this peak is occurring is not only the most probable state, it's also the the likeliest of all states that is going to happen. It's just like if you want to expect anything else besides the highest probability event, it's just like expecting a team of monkeys sitting in this room, and each monkey is given a typewriter, and you ask them to type something and you expect that they will produce the sonnets of Shakespeare. That's not going to happen. Even though it's physically possible that they come up with a sequence of typing that they produce the sonnets. There's nothing against physics that would not allow this to happen, but it's not going to happen because the probability is vanishingly small. So when we deal with large objects and we deal with the law of large numbers, the probability peaks somewhere. And where the probability peaks, that is the highest probability event or the highest probability distribution of energy, and it's also the only thing that's ever going to happen. Now when we deal with large numbers, there's a problem. The problem with large numbers is that they're large. You can't write them. If I would like to write 10 raised to power 15, I would have to put 1 and 15 zeros. It's going to take me time. And if I would like to count these atoms, it would probably take me more than 5 million years, which is the expected lifetime of our sun. So I'm not going to do that. So when we have very large numbers, we take the log. So instead of plotting sigma A, sigma B, omega A, omega B, and omega A multiplied by omega B, I would like to plot natural log omega A, natural log omega B, and natural log omega A, omega B, to make things look more reasonable. And that's what I've done in the simulation. Now look at these bottom curves. Please pay attention. Look at these bottom curves. This is raw omega A. Omega A is the number of microstates associated with A, with quantums in A on the x-axis. Now I take the logarithm of this curve. This is what I get. Now from a very large number, a huge number, I get a large number. This is about 250. It's still large, but not the kind of large we're talking about here. Now this is the logarithm of this curve. It starts off at a large number and then slopes downward. And this is the logarithm of this graph. Now this graph is monotonic. Do you understand monotonic? Monotonic means it's always increasing or always decreasing. It's monotonic, it's always increasing. This graph is also monotonic, it's always decreasing. But this graph is not monotonic, it's increasing and then decreasing. So it's peaking somewhere, just like this number of microstates, which is the number of possibilities, is peaking somewhere. So what we have is, it's peaking again at 67. So this object, which is the logarithm of this object, is called the entropy. This object is the entropy of system B. This object is the entropy of system A. And this object is the entropy of the total system, of the combined system, which comprises A and B. The entropy, remember one thing, entropy is the most, I can say it with fairly a good deal of confidence, it's the most subtle, the most poorly understood concept in all of physics, maybe in all of science. So if you understand it well, you're going to be in an elite class of physicists. Alright, so entropy is denoted by S, and it's equal to the total entropy, let's call it total, is equal to the natural log of the number of microstates, total number of microstates, and for historical reasons there is also some constant of proportionality with it, right, for historical reasons. Now could you tell me what are the dimensions of this quantity? It is dimensionless, no dimension. These are just the number of microstates. It's a number, it's dimensionless. So this on its own is dimensionless, but you add some constant of proportionality just due to history, and that constant of proportionality is called the Boltzmann constant. And this constant has units joules per Kelvin. So S has units joules per Kelvin. So the entropy represents the number of possible ways in which energy can redistribute in a system. The entropy number of ways in which energy can redistribute in a system. It's one possible definition of entropy. Another possibility is that entropy is the number of accessible microstates. Right? How many microstates are available? Another possibility is that entropy represents multiplicity. Now I'm going into semantics, or multiplicity means how many states are available. Okay? It's the antonym of unity. Unity means wahdat, multiplicity means kasrat. There's large number of states available, and if there are large number of states available, then the energy is large enough, it can redistribute in all of those states. So entropy is a measure of this multiplicity, and loosely, very loosely, people call it the degree of disorder. That's very loose, but these are more accurate descriptions. Right? These are more accurate. A scientific literate person would use these definitions. But if you would like to have a hand waving approach, then entropy is generally regarded as a degree of disorder. But I would not generally like this. Alright, another very interesting property is I can define SA, which is the entropy of system A. I can define SB, which is the entropy of system B. And S is it the sum of SA and SP? Yes, it is, because of the property of logs. And what is happening in this physical process? I'm going to move to the second law of thermodynamics now. We know when we've understood what entropy is. Now the second law of thermodynamics is that, let's look at it physically first. We brought two objects close to one another, and these objects are just talking to one another. They're not talking to the universe, to the surroundings. So it's a closed system. So there's some energy here, there's some energy here, right? And they are brought close together, and they would like to exchange this energy. Alright? So they're making a transaction. I'll give you better analogies tomorrow, but suppose energy is like money, and entropy is like happiness. And entropy is like happiness, and we live in a world in which it's a utopian world or an ideal world in which we would like the overall community to be happier. So we would like to exchange money in such a way that everyone is happier, that the whole community is happier. So objects would like to exchange energy such that the entropy is higher. The entropy goes to a higher value. Now these objects are brought close together. They exchange energy such that the entropy is the highest. And when they have enough time to exchange energy, which means thermal equilibrium has been established. Note this word. It's a technical word. Thermal equilibrium. When thermal equilibrium has been established, the entropy of the overall system is maximized. So when you're far from equilibrium, when you're very far away from equilibrium, suppose you start with object A has 20 quanta and object B will have 80 quanta. So you're starting off from here. You're starting off from somewhere here. It's a low entropy state overall. But then as you move towards equilibrium, slowly you move towards equilibrium, you stop here. At this point equilibrium has been established. And how do you know equilibrium has been established? Because the entropy is maximized. If you would like to go further, that is if A wants to be greedy and he wants to get more money, he wants to get more quanta, he wants to get more energy, the overall entropy of the system is going to decrease. And that's not favorable. Because these are happy beings. These are sentient souls. They would like to increase the overall happiness. So that state is only achieved when equilibrium is achieved. And the overall happiness has gone up. The overall entropy has gone up. So now I would like to write the second law of thermodynamics based upon the discussion we've had. Just like entropy can be defined in a number of ways, the second law of thermodynamics can also be written in a large variety of ways. And with the discussion that we've had so far, I would like to write it in these ways. First, if a system is away from equilibrium, thermodynamic or thermal equilibrium, it will move towards a condition of maximizing entropy. Very clear. Another possibility is that every closed system will try and will always succeed. Almost always succeed in maximizing entropy. एक मैं पहले सवाल पूछूं फिर आपका सुनता हूं. जो फर्स्ट लॉ ऑफ थर्मोडायनामिक्स है, क्या वो एक फंडामेंटल लॉ है? फंडामेंटल से मुराद ये है कि उसको एक्सपेरिमेंट से तो प्रूव और डिसप्रूव किया जा सकता है, लेकिन इज देयर एनीथिंग मोर बेसिक देन द फर्स्ट लॉ व्हिच कैन बी यूज्ड टू प्रूव द फर्स्ट लॉ? जी, it is the conservation of energy, but is it based on something simpler? No. We have to take it as an axiom that energy cannot be created or destroyed. Just like money. Energy is money. Money cannot be created or destroyed. If I give you money, you've given me something in return. Energy is just like money. It can change current, you can change currency, it can go from one form to another, but it cannot be created or destroyed. That's called inflation. So the first law of thermodynamics is really very fundamental. But the question I would like to ask you, and think about it for half a minute so that I can get some rest as well for half a minute, is the second law of thermodynamics fundamental? Just think about it. Fundamental really means that it's basic, it's axiomatic, it's can it be violated in some cases? So can the second law of thermodynamics be violated? Right, it's a probabilistic law, right? It's a probabilistic law. There's no question about that. We use probability and the law of large numbers to prove it or to verify it. But the point is that the probability of the most likely event, which has the largest number of microstates, is so high as compared to the alternatives that that's the only thing that's ever going to happen. So it is not as fundamental as the first law of thermodynamics. For example, when we talk about nanoparticles, they can share their energy in such a way that it's not an equitable distribution. I mean, there is still a finite probability that there's a 1 to 3 sharing or a 3 to 1 sharing when two atoms are brought close to one another. But that's not going to happen for the real very large objects that we generally deal with. So it is not fundamental in the same sense as the first law of thermodynamics, but for all practical purpose it's never going to be violated. ठीक है? इसलिए जब कुछ आपको पता है ना, पैटेंट्स होते हैं, इन्वेंशंस जब कोई करता है तो उसको पैटेंट किया जाता है कि जो इन्वेंटर है उसको राइट्स दिए जाते हैं, जुमला हकूक बहक मूजिद महफूज हैं, कोई और नहीं उसको चीज को बना सकता. ठीक है? तो बहुत से लोग कहते थे परपेचुअल मोशन मशीन्स और फर्स्ट लॉ को वायलेट करने की मशीन्स और सेकंड लॉ को वायलेट करने की मशीन्स बनाने की कोशिश की जाती है. तो पेटेंट ऑफिस ऐसी एप्लीकेशंस लेता ही नहीं है. क्यों नहीं लेता? फिजिक्स कहती है शायद कभी कभार 1 out of 10 is for 10 times ऐसा हो सके, but it's never going to happen. So second law of thermodynamics is not really as fundamental, but it can be treated as a fundamental law, and it's never going to be violated. The last thing I would like to talk about here, but there was a question. Yes, you got the point? Ji.
Sir, what I don't get is that entropy is sort of a degree of disorder, right? Loosely defined what it is. So why does the system want to maximize this degree of disorder? Won't it mean?
That's why I don't like the word disorder. An equitable distribution of energy, I don't like to call it disorder. I like to call it that energy has more room to go. If there's a few quantums of energy, and there are 3 people who walk into this room, and one possibility is that those 3 people are given just the front row to sit. That's one possibility. The number of microstates available is small. But if those three people would have the huge auditorium where they can be seated, that's a more, even though they will sit in a dispersed fashion, but that will make them happier. So that's why I don't like the word disorder. It's not really disorder, there is more space available for the quanta to go. And one question I would like to ask, why is this gone off at the wrong time? Zara ek minute wahan se karna padega. Why is this? Could you predict beforehand why this is 67%? Because of? Because of the quantity of atoms. Because it's the same ratio as the ratio of the atoms in the objects. So it depends upon the energy as well as the size of the object. If these were equally sized objects, the energy would really be shared 50-50. And that is why if I have a bouncing ball, so this bouncing ball here, even though this does not violate the first law of thermodynamics, it's not according to it's not in conformance to the second law of thermodynamics, because when the ball hits the ground, it wants to share its energy with the ground, and with every bounce it would like to share its energy with the ground. And when it shares energy with the ground, its own energy goes down. And eventually what happens is that there's an equal distribution of energy. The ball increases its thermal energy because of the collisions. The earth increases its thermal energy because of the collisions. So there is equitable distribution of energy. And that is why the reverse is impossible to happen. Improbable, and improbable to an extent that it's impossible. The second example I gave you. This reverse experiment, in which a large number of particles, they are combining and producing a very two fine beams, is not going to happen, because if you have a large number of particles, there are a large number of states available. There is lots of possibilities for the energy to be distributed. But if there are two fine beams, orderly beams approaching one another, there is not a large multiplicity of distributions of energy that are possible. But with a large number of particles being scattered, their energies can be shared in a large variety of ways, which means that the number of microstates is going to be very large, and therefore the higher entropy case is when there's a large number, there's a shower of particles. So fine beams collide and produce a shower of particles, but a shower of particles cannot congregate to produce a fine beam. In tomorrow's lecture, we're going to take our happiness entropy example further, and we're going to see what is temperature. So tomorrow is going to be a very important class. Thank you very much.